This is lecture 4, kinetic theory. In the previous lecture we looked at conservation laws, so we're interested in mass, momentum and energy conservation in this module, and we discussed that the fundamental form of these are in a Lagrangian frame, and we want to be able to use them as engineers in the Eulerian frame. So we made a few definitions about systems and environments and control volumes, and then we ended up working out the material derivative and the Reynolds transport theorem, and these are the tools that allow us to go and change this frame of reference. Okay, so we did it using conservation of mass, but we can do it, and we'll do it later on in our module, for conservation of momentum, conservation of energy. Okay, so today we're going to look at what is a fluid. How do you get from the motion of molecules to effectively the first law of thermodynamics. So what we're going to do is we're going to look at the motion of a single atom and then think about how all of the atoms in a box will move, and how do we relate those to temperature, to energy, enthalpy and work, and write an energy conservation law for these bunch of molecules bouncing around in a box. So students tend to get a bit confused about definitions here. So I'm using a very simple gas as a model here. So it's a single atom, it's not a molecule like air or CO2 or nitrogen, and it means that when you add energy to an atom, all it can do is move faster. It can change its kinetic energy. That's the assumption that we're making. For real gases, molecules, when you add energy to a real gas, these molecules go faster, but they also vibrate and rotate a little bit more as well. So some of the relationships, particularly the ones for CV and CP, they don't apply for normal gases for air that we're going to derive here. So just be careful about that when you start using this information to answer questions. Okay, so a little bit of history. So effectively what we're going to do is cover the last 350 years of developments in what's a fluid and how do you describe energy. So this is sort of potted history, if you like. So Daniel Bernoulli, back in the day, he decided that molecules existed, or atoms existed, and they move around in all directions, and they cause pressure. Nobody really knew what energy was at that time. They kind of thought that it was ether, and so energy was this kind of calorific fluid that kind of sort of flowed around. They didn't really link it with molecules, because they didn't know molecules existed. 1824, Sadi Carnot, when he was a PhD student in Paris, he 1820s, so people had started inventing steam engines. So they were used in mines to extract water, so the mines didn't flood, and they were horrendously inefficient. And Sadi Carnot thought about this, and he worked out where the inefficiency was. And he worked out that the inefficiency was because you are transferring heat between bodies at different temperatures, and this is a wasteful way of doing it, and you lose some efficiency. And he has an engine called the Carnot engine that we're going to come across in a few lectures' time, and this is the sort of the theoretical engine that can achieve maximum efficiency. Unfortunately, you can't build it, and so practical engines like petrol and diesel engines, their efficiency is measured with respect to a similar Carnot engine. And the difference between a Carnot efficiency and a real engine is really the measure of how efficient a practical heat engine can be. We came across James Joule, previous lecture. So he was interested in trying to work out the heat capacities of fluids, and we are going to define what the heat capacity is for a gas theoretically in this lecture. So James Maxwell, he made significant advances in the theory of what happens to molecules, and if they operate in a certain way, then we can come up with laws, and we can say a lot of things about the properties of a gas just from the way these molecules are bouncing around off each other and off walls. And we're going to concentrate on what he did in this lecture today. And then towards the end of the 1800s, heat engines were invented. So first came the spark ignition engine, or the petrol engine, and then later on the diesel engine came along, worked out by Rudolf Diesel. So these two engines are quite interesting because the Otto cycle is theoretically more efficient than the diesel engine, but on the practical case, when you actually run a diesel engine, the diesel engine is actually more efficient because of the way you can operate it. And Rudolf Diesel understood what the Carnot cycle was trying to tell him, and so he sort of out-designed Nicholas Otto. And we'll talk about that in a few lectures' time. And just a sort of final point, just to sort of make the point that nobody knew that atoms really were there. They were, all of this development that James Maxwell did, he did it just as a sort of a theoretical, hypothetical exercise, just to try and fit observations into or systemize observations. And it wasn't until the start of the 1900s that people started making measurements and could actually see the effect of molecules and gases. So most of the early work and early development on gases was purely experimental. So we had people sitting in research labs and just doing measurements at random, more or less, and they came up with observations. So Boyle's law and Charles's law, Avogadro and Clapeyron, these are all scientists who made observations and just said, this seems to be true. So there's no theory underlying it. It was just, I've done some experiments and all of my experiments tell me that this happens. So what's missing here is a kind of a theoretical framework for what these laws seem to be. And the problem really existed and sort of became manifest when people tried to measure temperature. So everybody knew what hot and cold was, and everybody wanted to measure it, have a sort of a way to saying, well, this is 3 times as hot as this, and so on. So most of the temperature scales were based around either air or water, because they're the two most common fluids, and water was used in steam engines at the time. But these are completely arbitrary measurements. So you could invent another temperature scale with melting point of cheese and the boiling point of sodium, and say there was 1,000 intervals between the two, and so all of these temperature scales were completely arbitrary. There was no physics in them. They were just a convenient way to measure something. But Kelvin came along and he said, well, this is not satisfactory. So he took lots of data from different people. So they measured the specific volume. So this is volume per mass, so 1 over the density. So he plotted the specific volume of a gas versus the temperature. And he found, depending on what the gas was, that the gradient was different, but they were all linear. And if you extrapolate the linear part all the way down, all of these gases crossed the V equals 0 axis at a certain temperature. And so he made the observation that at a certain magical temperature, all of these gases theoretically have 0 volume. And then he started thinking, and then he said, well, if the gas volume is defined by the motion of the gas molecules, then this temperature says that the molecules have no motion at this magic temperature. So what that meant was that the volume of the molecules themselves is actually irrelevant to the volume of the gas. And then he went on and he said, well, I'm going to relate the motion of the molecules to the energy of the gas. Okay, because he was saying, well, I'm going to say that the kinetic energy of the molecules is related to the energy of the gas and the temperature that the gas is at. So he said, right, I'm going to define another temperature scale. I'm going to call it Kelvin temperature scale, and it's a 1-point scale. So he had a bit of a problem because he said, well, here's my 0 Kelvin point, so I have no second point to reference. So he took the degree scale from the centigrade scale and just said, well, this is my 0, and I'm going to increment my temperature scale in degrees centigrade. So you end up with this equation here. And once he had made this leap between molecular motion and energy, this allowed him to do some further derivations and find out some more information. And we're going to go through these steps in a sort of a logical way. So we've got a box. We've got some molecules in there, and it's a simple low pressure gas. So by simple I mean they're only atoms. So the only energy that these atoms have is translational, is kinetic energy. So they don't vibrate, they don't twist. If you add some energy to them, they just go faster. That's the only thing. And it's low pressure, so the volume of if there was an effect of molecular interactions between molecules, then that's negligible. So simple low pressure gas, and we've got n molecules in our box, and they each have a mass m, and they have a whole bunch of random velocity components depending on whether they've hit each other or hit the wall or whatever. Okay, so we'll start off in a very simple way. We'll say, right, we're going to look at two surfaces of the box. This is the positive x direction, and my molecule, so I'm only going to look at one atom, and all it's going to do is it's going to oscillate in the x direction. So it's going to bounce off this wall, bounce off that wall, just a simple oscillator in that sense. Okay, and it's going at a certain speed, and it has a certain mass, so it has a certain momentum. And when it hits the wall, it's an elastic collision, so there's no loss of energy or momentum in the particle, so it comes off the wall at the same speed that it was approaching it. So there is a momentum change at the instant of the collision. Yeah? And that momentum change due to a single collision is twice the momentum of the particle. Okay? And then you can think, well, okay, so if there's a force that's being exerted on the wall, there must be a force holding that wall there. And if the force holding that wall wasn't there, and this molecule bounces off it, this wall would have to move. So so these collisions with the wall generate a force on the surface of this on the surface of the cube. And then we can do things like work out how often the wall is hit by the particle. So effectively it can do one transition for every given a certain velocity and a certain length. And for instance, if you make the cube half as big, you get twice the number of collisions. So we can work out the number of times per second the wall is hit by the particle. So this is the magnitude of the particle velocity in the x direction divided by 2 times the length. And so we can then work out how many momentum changes, if you like, or what's the sum total of the force on the wall due to a certain number of collisions per second. We end up working this out, and that's mu squared divided by L. And if we wanted to work out the pressure on the wall, so the pressure is the force divided by the area, and we know that the force is mu squared divided by L, and we know that the area is L squared because it's a box of side L. So mu squared divided by V is the pressure generated by a single particle hitting that wall if it's just moving in the x direction. Okay, so this is the result that we've got so far. So now what we need to do is we need to generalize that to all of the directions and all of the particles. So let's do that. So first of all, we start off by saying if we've got a particle moving in a random direction, if we wanted to work out the square of the speed of the particle, so this would be u squared, and that's going to be the sum of the square of the individual velocity components. So the easy way to think about this is in 2 dimensions, and if you've got a right angled triangle and you've got if you like, the x displacement of the triangle and the y displacement of the triangle, the hypotenuse is effectively the length of the speed of the particle. Yeah. Okay, so then let's say we've got n particles in the box, and what is the sum of the square of the speeds of the particles in the box? Okay, so we've got a particle un, and we sum up the square of the speed of all of the particles from n equals 1 to big N, which is the number of particles in the box. And from this definition up here, it's the sum of the squares of the individual velocity components, the x component, the y component, the z component. So we can write that as the sum of all of the x components squared plus the sum of all the y components squared plus the sum of all the z components squared. And then we say, well, this is a cubical box, and it doesn't matter which direction we look at it. It doesn't matter whether we're working out the pressure on the x or the y or the z coordinate. The pressure is always going to be the same. So that must mean that the x squared, the sum of all of the x squared components over all of the particles must be the same as the sum of all the y squared components, all the particles, and so on. So this means that when we write the sum of the actual speed of the particles, we can say, well, that's just 3 times the sum of all of the squares of any one of the velocity components. Okay. And then let's say we're interested in the mean kinetic energy of the particles. So this over bar here means this is a mean operator. So if I wanted to work out the height of trees in a forest, I'd have h1, h2, h3, h4, which would be the height of all the individual trees, and I'd sum all of those trees up, and then I'd divide by the number of trees, and that would give me h bar. So we can do that for the square of the speeds, and that's the sum of all of the squares divided by the number of particles we've got in our box, and as we've found out up here, this is just 3 times the sum of all of the components of one of the components divided by n, which is the number of particles in the box. Okay, so then we say, well, okay, we know what the pressure is related to one particle moving in our box in one direction, and that's that. So if we added up all of the particles moving in the x direction, we could work out the pressure due to that. That would be the sum of all the particles in the x direction. And then if we wanted to say, well, I'm interested in all of the particles moving in all of the directions, I can take this equation here, and I can say, well, the sum of all of my particles, the sum of the squares of the square of the velocities in the x direction is actually equal to n times u squared bar divided by 3. So I end up with something that looks a bit like this. Okay, so I substitute this thing into here, and we end up with a relationship like that. And I've added a 2 up here, and I've put a 2 down here, and the rest of it comes from this. Okay, And this thing in the bracket, this is the mean kinetic energy of my particles, half mu squared. Okay, so if all my particles were moving at the same speed, all of the mean kinetic energy would be this. And then we rearrange this slightly, and we end up with PV is equal to something to do with the mean kinetic energy of the particles and how many there are. Okay, so this is our first step in getting towards a gas law. So we've got PV, and then we've got something on the right hand side that we've got to sort out. So we need a law, or a fudge factor if you like, that relates kinetic energy of the particles to temperature. And this is what Boltzmann did, and he came up with something called the Boltzmann constant, and effectively this says, well, if you've got a certain number of joules of energy in terms of kinetic energy of the particles, that's worth a certain number of kelvins, if you like. So it's a fudge factor. So he said that his definition for his Boltzmann constant was the mean kinetic energy of the particles is 3/2 of the Boltzmann constant times T. And then when you substitute that into our proto-gas law that we have from the previous slide, we end up with an equation that looks a bit like this. So here we've got pressure and volume, and we've got the number of particles, we've got the Boltzmann constant, and we've now got temperature. So this is temperature in Kelvin. Okay, so we're nearly there with the gas law. So next stage is to get to our kind of familiar gas law, and we can do that using Avogadro's number, because there is a definition for Boltzmann constant that is that it's the universal gas constant divided by Avogadro's number, and this allows us to write the molar form of the gas law. So here n, small n, is the number of moles, and the number of moles is effectively the number of molecules we've got in our box divided by Avogadro's number. And this gives us a gas law which is PV nRUT, and nR subscript U is your molar gas constant, and it's a universal gas constant. It is independent of the type of gas that you're using, and it always has the same value. If you wanted to convert this to a mass-based gas law, you apply the molecular mass. So mu is the molecular mass. So this is the mass of a gas divided by how many moles of it you've got. And effectively what you do is you multiply and divide by the molecular mass, and you end up with PV is equal to mRT. So m is the mass in kilos, and R is the mass-based gas constant. And be careful with this, because this does depend on the type of gas. So the gas constant for CO2 and air and nitrogen, they're all different, and they're different because the mass gas constant is equal to the molar gas constant divided by the molecular mass. And this gives us our gas law, which we're quite familiar with, and we're going to end up using in this module. Okay. This also allows us to think about energy transfer. So if I wanted to heat up a gas, if we've got our box of molecules and I wanted to increase the temperature by a certain amount, how much energy would I need to transfer? So if or another way of saying, how much energy does my gas have? So EU is my definition for something called internal energy, and it's effectively the thermal energy of the gas. So this is defined by the number of particles multiplied by the mean kinetic energy of a particle, and we can use the Boltzmann constant to get from this to a temperature form, and then we can get rid of the Boltzmann constant by making use of the universal gas law, and we can get rid of the universal gas constant to the mass-based gas constant using the molecular mass, and we define this CV as 3/2 times the gas constant. So key point, it's only true for atoms. It's not true for air or N2 or CO2 or anything like that. Okay? So what CV does, what CV tells you is if I've got a gas and I'm not going to increase the volume of the gas when I heat it, and I want to heat it by a certain amount, say 10 Kelvin, what CV does, it tells you how much heat you have to add. Okay? It has a definition, which is this partial derivative, just so you're aware of it, but I'm not going to expect you to use this or derive this in this module. You can also heat a gas at constant pressure. So if you can imagine you've got a cylinder with a piston, and that piston has a weight on the top of it, and it's in equilibrium. So what that means is the weight acting down on the gas through the piston is balanced by the pressure on the other side of the piston surface pushing up. So the piston is stationary. So when you heat this gas, the temperature is going to go up and the pressure will go up, and because the pressure will go up, the piston will rise because the force pushing up is bigger than the weight pushing down. And then the volume of the gas expands, and then the pressure reduces, and eventually you get to a new equilibrium point where the pressure in the gas is equal, well, the force acting up through the pressure in the gas is equal to the weight acting down. Okay? So this is called constant pressure heating. And when you're heating a gas at constant pressure, the energy that you add is doing two things. The first thing it's doing is adding internal energy, like it was doing in constant volume. And the second thing it's doing is it's doing some work. It's pushing the piston. It's creating some volume in the gas. Okay? And you can work out how much work this gas is doing when it's being heated, because if you have a small element of work, this is the force on the piston from the gas, and the piston moves a small amount, and that force that's created by the pressure in the gas is the pressure times the area of the piston, and that gives you the volume, the pressure times, if you like, the change in volume of the gas. Okay? So if we say this is our gas law, and if we want to differentiate this during a constant pressure heating process, if we differentiate this term, the pressure stays the same, and we end up with a small change in volume, and we end up with a small change in temperature because the mass is the same and the gas constant is the same. So P dV is equal to mR dt. Okay, so the small element, the change in work, or the work done by the gas, is actually equal to mR dt. Okay, so when you add energy to a gas under a constant pressure, this energy that you add is called the enthalpy, and it has this EH sign. And this is the amount of energy you use to increase the temperature, and this is the amount of energy you use to increase the gas volume at constant pressure. And these two things together are related by m times Cp delta T. The Cp defines the enthalpy change of the gas. So if I wanted to increase the temperature of the gas by 10 degrees C, or 10 degrees Kelvin, say, if I knew what Cp was for the gas, I can work out directly how much energy I need to add to account for this thermal heating and the volume change. Okay, so this also has a partial derivative definition, but again, I'm not going to ask you to derive this or do anything with this. So these two things allow us to derive a conservation of energy equation. So let's go through the first line here and see what I'm trying to say. So what I've got here is I've got my specific internal energy change from state 2 to state 1. So this thing here is my change in internal energy from state 2 to state 1, and I represent that by EU1 to 2, and that will be the integral of this thing from temperature 1 to temperature 2. So the amount of energy I have to add to heat the gas from T1 up to T2 is this term here. Okay. And I can do the same with the enthalpy. So if I wanted to increase the temperature of the gas from T1 to T2 at constant pressure, it's this amount of energy I need to add, and we have the same nomenclature over here. Okay. So this allows me to come up with an energy conservation law. What I've got here is the enthalpy is equal to the internal energy change plus the work done. Okay, so what I can do is I can write that the enthalpy change, or if you like the heat transfer I have to add to the system to heat it at constant pressure, is going to be equal to the change in temperature of the gas plus the work done I have to do on that gas. Okay, and this allows us to define a general heat transfer law, and this is my general conservation of energy law. It's called the first law of thermodynamics, and the heat transfer that is applied is equal to the internal energy change plus the work done on this system. Okay, and this is known as the first law of thermodynamics, and this is what it looks like in specific terms. Okay, so we started off from an atom, we thought about how it moves, we ended up defining the gas law, we ended up working out what these specific heats are, we defined internal energy and enthalpy and work, and we put all of these things together into a general conservation of energy equation.